Good evening, and welcome to Story of the Cosmos. Tonight, we sit with a single, quiet question, one that has stretched astronomers' imaginations for over a century, and follow it all the way down. Suppose it happened. Suppose you were falling, right now, toward a black hole. What would it actually feel like? The honest answer is, it depends entirely on which one. Some black holes would end you long before you arrived anywhere near what most people picture as the edge, pulled apart, cell from cell, while the horizon itself was still hundreds of kilometers away. Others, the truly vast ones, the ones that sound the most fearsome, would let you cross their threshold feeling nothing at all. No violence, no warning, just an ordinary moment, indistinguishable from any other, and then a boundary quietly passed with the body still whole. That is the strange shape of this subject. Not one fate, but many, governed less by darkness or dread than by simple scale, mass, and distance. The smallest black holes are, in this one sense, the cruelest. The largest are, at least at first, almost gentle. We will walk through both kinds tonight, where the danger truly begins and where it doesn't. What the equations say, what the myths get wrong, and what still, even now, remains unknown. Every fall tells a different story. Imagine holding a piece of taffy between your hands, warm and soft, and pulling, not evenly, but because one end sits closer to something pulling harder than the other. That mismatch, that small difference in pull from one end of a thing to the other, is all gravity needs to reshape it. Astronomers call it tidal force, the same gentle imbalance that raises the tides on Earth's oceans, twice a day, without anyone noticing the mechanism behind it. Only here, stretched to an extreme that has earned a name of its own, spaghettification. Fall feet first toward a black hole, and your feet, closer to the source, are pulled harder than your head. Stretch that difference far enough, and a body becomes a thread. But how far is far enough? That depends entirely on where the boundary lies, and every black hole draws that boundary differently. For a black hole that does not spin, this boundary is described by the Schwarzschild radius, the distance from its center at which gravity becomes so complete that not even light, moving at its full speed, can climb back out. Cross that line, and you have crossed the event horizon. There is no return from there, and no way to see across it from outside. Only darkness, holding its shape against the stars behind it. Here is the puzzle worth sitting with, though. That radius grows in a simple, straight line with mass. Double the mass, double the radius. But the stretching force, the tidal pull that does the actual damage, does not follow along so politely. It falls away with the cube of the distance and rises only with the mass itself, once, not doubled or tripled. Work through what that means, and something strange appears. The very thing that makes a black hole massive is the same thing that, at its horizon, makes the stretching gentler. So the puzzle stands like this. Two objects can share the same name, the same fundamental nature, and still promise entirely different endings. One where the danger arrives long before the boundary ever does. One where the boundary arrives, and nothing happens at all. Same fall, same equations, different story entirely. Karl Schwarzschild was a German artillery officer stationed on the Russian front in the winter of 1915. Around him, trenches, the ordinary machinery of a war that would kill millions. And somewhere in the middle of it, on whatever paper he could find, he worked through Einstein's newly published field equations and produced something no one had managed before, an exact solution. A precise geometry for the space around a single point of mass. He mailed it to Einstein himself. Einstein, by his own account, had not expected anyone to solve the problem so simply, so completely, so soon. Einstein presented the soldier's pages to the Prussian Academy of Sciences on his behalf, crediting a man still in uniform. Schwarzschild never saw where his own equations were leading. Within months, on that same front, he developed a rare and painful autoimmune disease of the skin. He was sent home in March of 1916. He died 2 months later, in May, at 42 years old. And he died, by most accounts, without ever believing his own solution could describe something real. To him, the strange point his mathematics pointed to, where distances collapse and describe nothing anyone could stand near, was a curiosity of the numbers, not a place. He is reported to have called it simply, physically meaningless. He was not being careless. He had no way to know. The equation was sound long before anyone had a reason to trust what it was quietly describing. And it would be the better part of a century before the rest of the world caught up to what he'd written from a trench, almost as an afterthought between one battle and the next. He gave us the shape of the fall. He never got to see it confirmed. Falling toward a body the size of the Sun, compressed into 3 kilometers, the danger arrives long before the boundary does. At around 700 kilometers out, still a comfortable distance in cosmic terms, farther than most countries are wide, the pull on a falling body's near side would already outmatch the pull on its far side by enough to shatter bone. Close that gap to 100 kilometers, and the difference between what your head feels and what your feet feel would reach something like 6 million times what gravity does to you standing still on Earth. Human tissue lets go at a fraction of that. The horizon, that famous edge past which nothing returns, would still be nearly 100 kilometers away when the unmaking was already finished. This is the part the size comparison gets backwards. It's tempting to think smaller means safer, a compact object, easier to avoid, less to fear. The mathematics says the opposite. Tidal force depends on how sharply gravity changes over a short distance, and near a small, dense black hole, gravity changes very sharply indeed. Cygnus X1, one of the first black holes ever identified, drifting through the constellation of the Swan, some 7,000 light-years away, holds around 21 times the Sun's mass in that same, brutally small space. A body falling toward it would be drawn into a thread of plasma before it ever crossed the horizon, the destruction finished, the boundary still ahead, waiting for nothing. There is a strange comfort buried in this, even so. It means the smallest black holes, the ones that sound almost modest next to their monstrous cousins, are in truth the least forgiving place in this whole account. And it means the question worth asking is never simply how large the darkness is. It's how tightly that mass has been drawn together, because that, far more than size alone, is what decides how far out the ending begins. Small holds no mercy at all. Falling towards something small, then, is not a slow approach. It is an ending that arrives early, in the dark, long before any horizon comes into view, and it would be reasonable to assume the opposite is also true. That larger, more famous black holes must be worse, hungrier, reaching further out to claim whatever wanders near. This is one of the oldest misunderstandings about them, and it is worth setting down gently. Beyond its horizon, a black hole pulls on the universe exactly as any other object of the same mass would. Nothing more. If the Sun itself were quietly replaced by a black hole of equal mass, Earth would notice only the loss of light and warmth. Its orbit, its year, its seasons would continue exactly as before. There is no reaching, no pulling things in against their will. Only the same gravity that has always governed falling apples and orbiting moons, applied here to something that happens not to let its light back out. A second comfort, less obvious than the first. Watch someone fall toward a black hole from a safe distance, and they will seem to slow. Their light will stretch, redden, dim, approaching the horizon but never, in your patient watching, quite arriving. It is tempting to imagine them frozen there forever, pinned to the edge for all time. But the dimming has a limit. Within a finite span, ordinary and measurable, the light fades past any instrument's ability to catch it, and the image is simply gone. Nothing is preserved at the threshold. It only appears that way from outside, for a while. And one more, gentler than it sounds. The idea that falling in means glimpsing the universe's entire future in a single blinding instant, every star's death, every ending, arriving at once, does not hold. A falling traveler receives only the light that has already been sent, light that manages to catch them before the story closes. The future they never had time to inherit simply never arrives. What's left is quieter than the myths. Ordinary gravity, a fading, not a freezing, a future left unseen, not devoured. Falling toward Sagittarius A, at the center of our own galaxy, tells almost the opposite story. 4.3 million times the mass of the Sun, wrapped in a horizon some 12 million kilometers in radius. Cross that boundary, and the difference in pull between your head and your feet would come to only about 0.02% of what you already feel standing here, on Earth. Imperceptible. There would be no flash at the threshold, no wall, no sensation marking the line. Just space, continuing. Scale up again to M87, the black hole in the very first image ever taken of one, released in 2019. 6.5 billion suns, folded into a horizon nearly 140 times the distance from Earth to our own Sun. Wide enough that it alone is larger across than our entire solar system. And here, the mathematics takes its strangest turn. A black hole's horizon grows in step with its mass, but the volume it encloses grows with the cube of that radius. So the biggest black holes are, on average, among the least dense objects of their size anywhere. Past a certain point, somewhere around 10 million solar masses, a black hole's average density falls below that of water. Larger still is Ton 618, among the most massive black holes known, somewhere between 40 and 66 billion suns, depending on which measurement is trusted, 10,000 times heavier than the black hole at the center of our galaxy. At that scale, spaghettification does not happen at the threshold at all. It waits. A falling body could cross the horizon whole, intact, unaware, and only be pulled apart much later, deep inside, long past where anyone watching from outside could ever know. So the danger does not scale the way it first seems it should. The smallest black holes kill from hundreds of kilometers away. The largest ones let you in first, and ask their questions after. A NASA supercomputer once tried to put a number on that mercy, and the number is stranger than any guess. Researchers at Goddard Space Flight Center built a simulation of a camera falling toward a black hole the size of Sagittarius A, 4.3 million times the mass of the Sun, its horizon nearly 8 million miles in radius. In the camera's own time, the fall to that horizon takes about 3 hours, spiraling through almost 2 long, slow orbits on the way down. Nothing violent, nothing sudden. Then the horizon is crossed. And 12.8 seconds later, measured from inside that falling frame, the tidal forces finally close in, tearing the camera apart some 128,000 kilometers short of the center. What remains reaches the singularity in a fraction of a heartbeat. The same simulation modeled a gentler pass, a camera swinging near the black hole at 60% of the speed of light, then escaping outward again. Over 6 hours as measured far away, the camera itself experiences 36 minutes less. No spacecraft has ever done this, but the mathematics that describes it is the same mathematics, confirmed again and again by everything astronomers have watched black holes actually do. And they have watched. In November of 2014, X-ray telescopes caught a supermassive black hole, a few million times the Sun's mass, pulling apart a star 3 times our Sun's size, 290 million light-years away. Astronomers watched the debris settle into a new disk of glowing gas in something like real time. A few years earlier, in March of 2011, a black hole, roughly 8 million solar masses, tore apart a star nearly 4 billion light-years distant, and in doing so, launched a jet of matter moving faster than 9/10 the speed of light. A jet that happened to point almost exactly at Earth, which is the only reason we noticed it glowing in X-rays for months afterward. These were not illustrations. They were not renderings on a supercomputer. They were real stars, in real galaxies, coming apart in real time, their light crossing hundreds of millions of years of empty space just to tell us it happened. The simulation and the sky agree with each other. That is a rare and quiet kind of confirmation. Falling into a black hole feels like slow disappearance, but seeing one at all took something entirely different. Years of patient, coordinated attention. The image of Sagittarius A star, released on the 12th of May, 2022, was the second black hole ever photographed, following one 3 years earlier at the heart of a galaxy called M87. Both came from the same instrument, if it can even be called one instrument, the Event Horizon Telescope, a network of radio observatories scattered across the planet, from the high desert of Chile to the ice of the South Pole, linked together so precisely that they behaved as a single eye the size of the Earth itself. Sagittarius A star should have been the easier target. It is our own galaxy's center, close by cosmic standards. But its gas moves fast, completing a full orbit in perhaps half an hour. So, where M87's black hole held still for its portrait over days, Sagittarius A star kept shifting mid-exposure, flickering and rearranging itself while astronomers were still trying to look. It took new techniques, built specifically to average across thousands of possible images, just to hold something so restless still enough to see. And the data itself was gathered in April of 2017, 5 years before the world saw the result. 5 years of cross-checking, of independent teams working from the same raw signal without comparing notes, so that when they finally did compare, the agreement itself would mean something. There is a particular kind of devotion in that. Not the drama of a single breakthrough, but the slower work of many people on many continents, pointing instruments at the same patch of sky at the same coordinated moment, waiting for light that had already given up trying to reach them, asking it to stay just long enough to leave a trace. What came back was a ring of light bent around a shadow, a boundary gently drawn around the place where the falling and the timing and the equations all meet. They had gone looking for an absence. What they found was a portrait. Falling feet first, no one comes back to tell you what a horizon is like at the far end. Everything in this hour, the stretching, the light bending into a ring, the 3 hours and 12 seconds inside a supercomputer's careful arithmetic, describes the approach. None of it describes the arrival. A black hole that spins, and by every observation nearly all of them do, is not expected to end the way the simplest equations first suggested, a single point where everything simply stops. Some models of a rotating black hole's interior describe a second, inner horizon in the idealized models, though whether it could survive inside a real black hole is deeply uncertain, tucked inside the outer one, somewhere past the horizon and short of the center. What waits beyond that boundary is not something anyone has measured. It is not something anyone can measure, not yet, not with because no light, signal, or information can ever return from beyond the horizon. Karl Schwarzschild wrote down the geometry for all of this in a matter of weeks from a trench between calculations for artillery ranges, and he died within the year, still doubting that any of it could be real. A century of careful, patient looking, X-ray telescopes catching real stars torn open, a planet-wide array holding steady long enough to draw a shadow, has since strongly supported much of what his equations predicted. The horizon is real. The stretching is real. The gentleness of the largest thresholds is real. The singularity itself, what it is, whether point or ring or some shape general relativity was never built to name, remains a question the equations ask without answering. Not a gap waiting to be filled by better instruments next year. A place where two great descriptions of the universe, gravity and the quantum world, are known to disagree, and no one yet knows which one bends. So the honest ending is not an ending. Something is there. What it is still dark. This has been a story of the cosmos. Out there, the stories go on, slowly, quietly, as they always have. Let this one drift on without you, until the next journey.